On December 27, 2004, at 21 hours 30 minutes and 26 seconds Coordinated Universal Time, a wavefront of electromagnetic radiation arrived at Earth that was unlike anything previously recorded by human instruments. The source was a compact stellar remnant catalogued as SGR 180620, located in the constellation Sagittarius at an estimated distance of roughly 50,000 light-years from the solar system, meaning the radiation had been traveling across space for approximately 50 millennia before it intersected with the orbital path of Earth. Within the span of about 0.2 of a second, the initial spike of this event delivered more energy in the form of gamma rays than the Sun emits across the entire electromagnetic spectrum in approximately 250,000 years. That single statement requires careful unpacking, because the numbers involved are so far removed from everyday experience that they risk becoming meaningless if presented without context, and the phenomenon itself sits at the intersection of several distinct domains of astrophysics that developed largely independently of one another over the course of the 20th century before converging, somewhat unexpectedly, on the physics of a class of objects that were not even theorized to exist until 1979, and not widely accepted as real until the mid-1990s. To understand what SGR 180620 is, what happened on that December day, and why this event remains significant for physics, it is necessary to begin not with the event itself, but with the category of object that produced it, and before that, with the broader class of stellar remnant to which that object belongs, and before that, with the physical processes that create such remnants. Stars more massive than roughly 8 to 10 times the mass of the Sun do not end their lives quietly. After exhausting the nuclear fuel in their cores, progressing through successive stages of fusion from hydrogen to helium to carbon and onward through neon, oxygen, and silicon, they eventually develop an inert core composed primarily of iron group elements. Iron is the most tightly bound nucleus in nature in terms of binding energy per nucleon, which means that no further energy can be extracted through fusion. When this iron core exceeds a critical mass, roughly 1.4 solar masses, depending on conditions, electron degeneracy pressure can no longer support it against gravity. The core collapses in a fraction of a second, reaching densities comparable to those of atomic nuclei, at which point the strong nuclear force and neutron degeneracy pressure halt the collapse and produce a rebound shockwave that, assisted by neutrino heating and various hydrodynamic instabilities, ejects the outer layers of the star in what is observed as a core collapse supernova. What remains at the center, in many cases, is a neutron star, an object with a mass between roughly 1.1 and perhaps 2.3 solar masses, compressed into a sphere approximately 20 to 25 kilometers in diameter. The densities involved are staggering, on the order of several 100 million tons per cubic centimeter in the outer core, rising to perhaps 1 billion tons per cubic centimeter or more in the innermost regions, where the actual state of matter remains one of the major unsolved problems in nuclear physics. The gravitational binding energy released during this collapse is enormous, on the order of 3 × 10⁻46 joules, and the vast majority of this energy is carried away by neutrinos, with only a small fraction going into the kinetic energy of the ejector, the electromagnetic radiation of the supernova, and the residual heat and rotational energy of the neutron star. The surface gravity of a neutron star is approximately 2 × 10⁻11 meters per second squared, which is about 200 billion times the gravitational acceleration at Earth's surface. The escape velocity from the surface is roughly 1/3 the speed of light. These are conditions under which general relativistic effects are no longer small corrections, but fundamental features of the physics. Neutron stars were first predicted theoretically by Walter Baade and Fritz Zwicky in 1934, barely 2 years after the discovery of the neutron itself by James Chadwick in 1932. Baade and Zwicky proposed that supernovae represented the transition of ordinary stars into neutron stars, and that this process released enormous amounts of energy, a prescient suggestion that was largely ignored by the wider physics community for decades. The theoretical framework for understanding the structure of neutron stars was developed independently by J. Robert Oppenheimer and George Volkoff in 1939, who used the equations of general relativity combined with a simplified equation of state for neutron matter to calculate an upper mass limit for stable neutron stars. Their work showed that above a certain mass, no known force could prevent further collapse, a finding that pointed toward what would later be understood as black holes. But the observational confirmation of neutron stars did not come until 1967, when Jocelyn Bell Burnell, then a graduate student working under Anthony Hewish at Cambridge, detected regular pulsed radio signals from what turned out to be a rapidly rotating neutron star, soon termed a pulsar. The regularity of these pulses was initially so extraordinary, with periods stable to parts in a billion, that the possibility of artificial origin was briefly considered. A historical episode that illustrates how unexpected the discovery was within the context of the observational astronomy of the time. By the early 1970s, pulsars were well established as rapidly rotating, highly magnetized neutron stars. The basic model, proposed by Thomas Gold in 1968, holds that the neutron star possesses a strong dipolar magnetic field, typically on the order of 10 to the 8th to 10 to the 9th Tesla, with its magnetic axis misaligned relative to the rotation axis. Charged particles accelerated along the magnetic field lines emit beamed radiation, and as the star rotates, this beam sweeps across the observer's line of sight like a lighthouse, producing the observed pulsations. The rotational energy of the neutron star powers the emission, and the star gradually spins down as it loses energy, a prediction confirmed by the observed increase in pulse period over time for most pulsars. By the late 1970s, several hundred pulsars had been catalogued. Their properties were reasonably well understood within this framework, and the physics of neutron star interiors, surfaces, and magnetospheres had become a well-defined subfield of theoretical astrophysics. But not all neutron stars behave as ordinary pulsars. In March of 1979, a series of events occurred that would eventually lead to the recognition of an entirely new class of neutron star, one whose properties were so extreme that they required a fundamentally different physical mechanism to explain. On March 5, 1979, a burst of gamma rays and hard X-rays, lasting only about 0.2 of a second at its peak, followed by a decaying tail of softer pulsating emission lasting several minutes, was detected by multiple spacecraft in the interplanetary network of gamma-ray detectors then operating. The source was subsequently localized through triangulation to a position coincident with a supernova remnant in the Large Magellanic Cloud known as N49. This event, initially designated GRB 790305b under the conventions for gamma-ray bursts, was extraordinary for several reasons. Its peak luminosity, if the distance to the Large Magellanic Cloud was approximately 167,000 light-years, was roughly 10 to the 38th watts, or about 10 to the 11 times the luminosity of the Sun, concentrated in the gamma-ray band and compressed into a fraction of a second. The pulsating tail showed a clear periodicity of approximately 8 seconds, strongly suggesting that the source was a rotating compact object, most likely a neutron star. The spectral characteristics differed sharply from those of classical gamma-ray bursts, which at that time were a profound mystery with no widely accepted physical model. This event of March 5, 1979, became the prototype for a new class of high-energy transient, though its significance was not fully appreciated for years. In the following years, 2 additional sources were identified that produced repeated bursts of soft gamma-ray emission, distinguishing them from the vast majority of gamma-ray bursts, which were one-time events. These recurrent sources were designated soft gamma repeaters, abbreviated as SGRs, precisely because their emission was softer, meaning lower in photon energy than that of the classical gamma-ray bursts, and because the same source produced multiple bursts over time. By the early 1990s, 3 soft gamma repeaters had been identified: SGR 052666, associated with the March 1979 event; SGR 180620, discovered in 1979 through a series of recurrent bursts detected by the CONUS experiment on the Venera 11 and Venera 12 spacecraft; and SGR 1900 Plasma-Boise, identified through bursts detected in the early 1980s. A fourth, SGR 162741, was discovered later in 1998. SGR 1806-20 itself was first recognized as a distinct source through its bursting activity. The designation follows the convention for high-energy sources, with the numbers representing the approximate right ascension and declination of its position on the sky. 18 hours and 6 minutes right ascension, minus 20 degrees declination, placing it in the direction of the galactic center. Early observations established that the source was located behind a significant column of interstellar dust and gas, which heavily absorbed its emission at lower energies, making it essentially invisible in optical and ultraviolet wavelengths. Its detection and study were therefore entirely dependent on instruments sensitive to X-rays and gamma rays, technologies that matured substantially during the 1980s and 1990s with the deployment of increasingly sophisticated space-based observatories. The physical interpretation of soft gamma repeaters was the subject of considerable debate during the 1980s. Several models were proposed, including accretion onto neutron stars in binary systems, collisions between neutron stars and comets or asteroids, and various instability mechanisms in neutron star crusts and magnetospheres. The theoretical landscape changed dramatically in 1992 with the publication of a paper by Robert Duncan and Christopher Thompson, then at Princeton University and the Canadian Institute for Theoretical Astrophysics respectively, which proposed the existence of a new class of neutron star possessing magnetic fields far stronger than those of ordinary pulsars. They calculated that under certain conditions, during the formation of a neutron star, specifically when the convective motions in the hot, newly formed neutron star are vigorous enough and the rotation period is short enough, an efficient helical dynamo mechanism could amplify the magnetic field to values of 10 to the 11 Tesla or even higher, roughly 1,000 times stronger than the fields of ordinary radio pulsars. They named this hypothetical class of objects magnetars. To place this in perspective, the strongest sustained magnetic fields achievable in terrestrial laboratories are on the order of about 45 Tesla for continuous fields and roughly 1,000 Tesla for pulsed fields lasting microseconds. The magnetic field at the surface of a typical radio pulsar is about 10 to the 8 Tesla. The magnetic field proposed for magnetars, 10 to the 11 Tesla, is roughly 10,000 times stronger than that of an ordinary pulsar, and more than 1 billion times stronger than anything achievable in a laboratory. At such field strengths, the physics of matter and radiation is profoundly altered. Atoms are compressed into elongated needle-like shapes aligned with the field. The vacuum itself becomes birefringent, meaning that it acquires different refractive indices for different polarizations of light, an effect predicted by quantum electrodynamics but unobservable under laboratory conditions. The magnetic pressure, which scales as the square of the field strength, far exceeds the structural strength of the neutron star crust, meaning that the magnetic field can stress, crack, and rearrange the crust in events that release enormous amounts of energy. Duncan and Thompson developed their magnetar theory in a series of papers through the 1990s, providing increasingly detailed models for how the decay and reconfiguration of ultra-strong magnetic fields could explain the observed properties of soft gamma repeaters. The basic mechanism proposed for ordinary SGR bursts involves the buildup of magnetic stress in the neutron star crust, analogous in certain respects to the buildup of tectonic stress in Earth's crust before an earthquake, though the analogy should not be taken too literally. When the stress exceeds the breaking strain of the crust, a fracture occurs, a starquake, which suddenly rearranges the surface magnetic field. This releases energy in the form of trapped fireballs of electron-positron pairs and photons confined by the magnetic field near the surface. For ordinary bursts, the energies involved range from roughly 10 to the 34 to 10 to the 37 joules, comparable to or exceeding the total energy output of the Sun over days to years, but released in fractions of a second. These ordinary bursts, while individually impressive, are far less energetic than the giant flares. The giant flares represent a qualitatively different phenomenon. The March 5, 1979 event from SGR 052666 was the first recognized giant flare. No comparable event was observed for nearly 2 decades, which severely limited the ability to study this phenomenon. Then, on August 27, 1998, SGR 1900+14 produced a giant flare that, while less luminous at its peak than the March 1979 event, was observed with far more sophisticated instrumentation and provided crucial data for testing the magnetar model. The August 1998 flare had a peak luminosity of roughly 10 to the 37 watts and produced measurable effects on Earth's ionosphere, a remarkable circumstance given the source's distance of roughly 20,000 light-years. The pulsating tail showed a period of 5.16 seconds, consistent with the spin period of the neutron star, and the spectral and temporal evolution matched the predictions of the magnetar model in considerable detail. This event did much to establish the magnetar interpretation as the leading model for soft gamma repeaters. But the event of December 27, 2004, from SGR 1806 to 20, dwarfed both previous giant flares by a very large factor. The peak isotropic luminosity of this event has been estimated at roughly 10 to the 40 watts, making it approximately 100 times more luminous than the August 1998 flare from SGR 1900+14, and roughly 10 times more luminous than the March 1979 event from SGR 052666, after accounting for the difference in distances. This single event released more energy in its initial spike than the Sun would emit in approximately 250,000 years. To state this differently, if the same event had occurred from a magnetar located at the distance of the nearest known neutron star, which would be only a few hundred light-years away, the energy flux at Earth would have been sufficient to cause significant damage to the ozone layer and potentially to trigger a mass extinction. Even at 50,000 light-years, the event produced measurable effects. The detection of the December 2004 event was made by essentially every operational gamma-ray and X-ray satellite in orbit, as well as by ground-based instruments sensitive to its indirect effects. The initial hard spike saturated the detectors of most gamma-ray instruments, meaning that the true peak flux was initially difficult to determine because the instruments were not designed to handle such an extreme input. The Burst Alert telescope on the Swift satellite, which had been launched only a month earlier, was saturated. The RESI solar X-ray satellite, which was on the opposite side of Earth from the source at the time of the initial spike, and therefore should have been shielded from the direct emission, nevertheless detected the event through gamma rays that had reflected off the Moon, a detection path that was unprecedented and that speaks to the extraordinary intensity of the radiation. The CONUS instrument on the WIND spacecraft, the integral satellite of the European Space Agency, the Russian Koronas F Solar Observatory, and numerous other instruments all recorded the event, each providing data in different energy ranges and with different temporal resolution. The temporal profile of the event was broadly similar to those of the two previous giant flares, but with important differences in detail. The initial spike lasted approximately 0.2 of a second and contained the vast majority of the total energy. This was followed by a pulsating tail lasting several hundred seconds, modulated at the 7.56-second rotation period of the neutron star. The tail emission was softer in spectral terms than the initial spike and showed a complex evolving pattern of pulse profiles, with the shape of the pulse changing from cycle to cycle in a manner consistent with a trapped fireball of hot plasma confined by the magnetar's magnetic field, gradually cooling and shrinking as it radiated energy. The total energy in the pulsating tail was estimated at roughly 10 to the 38 joules, itself an enormous quantity, but only about 1% of the energy in the initial spike. The initial spike presented particular challenges for physical interpretation. The spectrum during the spike was extremely hard, meaning it was dominated by high-energy photons, with significant emission extending to energies above 1 mega-electron-volt. The rise time was remarkably fast, less than a millisecond, which places constraints on the size of the emitting region through light travel time arguments. The emitting region could be no larger than a few hundred kilometers, consistent with emission from the immediate vicinity of the neutron star. The peak luminosity during the spike greatly exceeded the Eddington luminosity, which is the theoretical maximum luminosity at which radiation pressure balances gravitational attraction for a spherically symmetric source. For a neutron star of 1.4 solar masses, the Eddington luminosity for normal electron-photon interactions is about 10 to the 31 watts. The observed luminosity exceeded this by roughly 9 orders of magnitude, which means that the radiation could not have been isotropic, or the emission mechanism was fundamentally different from thermal radiation interacting with ordinary matter, or both. In the magnetar model, the ultra-strong magnetic field suppresses the cross-section for photon-electron scattering, for photons polarized in one of the two modes, the ordinary mode, effectively raising the Eddington limit by a factor that depends on the field strength and geometry. Additionally, the emission may have been somewhat beamed rather than perfectly isotropic, which would reduce the inferred total energy by some factor, though analyses of the pulsating tail suggest that the beaming factor was moderate, not extreme. The physical model that best accounts for the giant flares involves a catastrophic large-scale rearrangement of the magnetar's internal and external magnetic field. Unlike the ordinary bursts, which are attributed to localized crustal fractures, the giant flares are thought to result from a global instability in which the magnetic field threading the neutron star interior undergoes a sudden reconfiguration, releasing energy stored in twisted magnetic field configurations that had built up over years or decades. The analogy that is sometimes drawn is to a solar coronal mass ejection, or a large solar flare, but this analogy is only approximate because the magnetic field strengths, the densities, and the physical conditions in a magnetar magnetosphere are radically different from those in the solar corona. In the magnetar case, the initial energy release produces a pair-photon fireball, a region of extremely high temperature and density filled with photons, electrons, and positrons in approximate thermal equilibrium, trapped by the closed magnetic field lines near the stellar surface. This fireball is initially opaque to its own radiation and cools gradually as it expands and becomes transparent, producing the observed pulsating tail as different parts of the fireball come into and out of the observer's line of sight due to the rotation of the neutron star. The initial spike is thought to correspond to the moment of the magnetic reconfiguration itself, when a portion of the fireball, or the relativistically expanding ejector, momentarily exceeds the trapping capacity of the magnetic field and escapes as a rapidly expanding shell of radiation and electron-positron pairs. This expanding shell, moving at a substantial fraction of the speed of light, produces the hard initial spike observed by distant detectors. As the shell becomes optically thin, the emission ceases rapidly, giving the spike its short duration. Meanwhile, the portion of the fireball that remains trapped near the surface continues to emit in the pulsating tail. The energy source for this entire process is the magnetic field itself. The total magnetic energy stored in and around a magnetar can be estimated from the field strength and the volume of the neutron star. For a dipolar field of 10 to the 11 Tesla threading a neutron star of radius 12 kilometers, the stored magnetic energy is on the order of 10 to the 40 joules or greater, depending on the configuration and on how much of the energy resides in the interior versus the exterior of the star. The energy released in the December 2004 giant flare, roughly 10 to the 39 to 10 to the 40 joules in the initial spike, thus represents a significant fraction of the total stored magnetic energy, suggesting that the event involved a major and possibly irreversible change in the magnetic field structure. If this is correct, one would expect such events to be rare for any given magnetar, occurring at most a few times over the active lifetime of the source, which is estimated to be on the order of 10,000 years, based on the rate at which the ultra-strong magnetic field decays through various dissipation mechanisms. This last point connects to the broader question of magnetar evolution and demographics. The active lifetime of a magnetar is much shorter than the typical ages of ordinary radio pulsars, which can remain active for millions of years. The ultra-strong magnetic field of a magnetar decays primarily through processes in the neutron star crust and core, including ohmic dissipation, ambipolar diffusion, and Hall drift, and this decay provides a continuous source of internal heating that manifests as persistent X-ray emission even between bursts. The persistent X-ray luminosity of SGR 180620 before the December 2004 event was approximately 10 to the 28 watts, which is several orders of magnitude higher than expected from a neutron star of comparable age cooling passively without an internal heat source. This persistent emission is one of the key observational signatures of magnetars and was one of the early pieces of evidence supporting the magnetar interpretation. The spin-down rate of SGR 1806-20 also provides crucial evidence. The neutron star's rotation period of 7.56 seconds is far longer than the millisecond periods characteristic of young pulsars, and its period derivative, the rate at which the period is increasing, is approximately 10 to the minus 11 seconds per second, which is far higher than that of typical radio pulsars. In the standard magnetic dipole model for spin-down, the rate of rotational energy loss is proportional to the fourth power of the magnetic field strength divided by the cube of the rotation period. From the measured period and period derivative, one can infer a surface dipolar magnetic field strength for SGR 1806-20 of roughly 8 times 10 to the 10 Tesla, which is in the range predicted by the magnetar model. This inferred field strength should be understood as a lower bound on the true surface field, because higher-order multipole components of the field, which fall off more steeply with distance and therefore contribute less to the spin-down torque, may carry comparable or even greater energy. The characteristic age, defined as the ratio of the period to twice the period derivative, is roughly 1600 years for SGR 1806-20, suggesting that the neutron star is relatively young, though the characteristic age should be treated with caution because it assumes constant spin-down and a birth period much shorter than the current period, assumptions that may not hold for magnetars given the complexities of magnetic field evolution. The distance to SGR 1806-20 has been the subject of extended discussion in the literature, and this is worth examining because the inferred energy of the December 2004 event depends directly on the square of the assumed distance. The source is located in the direction of the galactic center, behind substantial columns of interstellar gas and dust, which makes parallax measurements extremely difficult. The most commonly cited distance estimate is approximately 50,000 light-years, or roughly 15 kiloparsecs, based on several lines of evidence. First, SGR 1806-20 appears to be associated with a cluster of massive stars, including several extremely luminous blue variables and Wolf-Rayet stars, whose properties suggest a distance in the range of 9 to 15 kiloparsecs. Second, the hydrogen absorption column and the dispersion measure for sources observed in radio wavelengths are consistent with a distance of this order. Third, in 2005, observations of a radio afterglow from the December 2004 event, conducted with very long baseline interferometry, detected an expanding radio nebula whose angular expansion rate, combined with assumptions about the expansion velocity, yielded a distance estimate consistent with approximately 15 kiloparsecs, though with significant uncertainties. Some authors have argued for a somewhat shorter distance, around 6 to 9 kiloparsecs, which would reduce the inferred energy by a factor of several. Even with the lower distance estimate, the event remains by far the most energetic burst from a source within the Milky Way ever recorded and retains its status as the most powerful explosion detected from a compact stellar object. It is worth pausing here to clarify the distinction between the December 2004 event and other astrophysical explosions that might be described as more powerful in certain respects. Supernovae, for instance, release total energies on the order of 10 to the 46 joules, far exceeding the energy of the magnetar giant flare. Gamma-ray bursts, which are now understood to arise from the collapse of massive stellar cores or the mergers of compact objects, can release 10 to the 44 joules or more in relativistic jets and gamma-ray emission. The December 2004 giant flare from SGR 1806-20, with a total energy of roughly 10 to the 39 to 10 to the 40 joules, is many orders of magnitude less energetic than these events in terms of total energy release. What made it extraordinary was not the total energy, but the peak luminosity, the rate of energy release. For a brief fraction of a second, SGR 1806-20 was the most luminous object in the observable universe in terms of the rate of photon emission reaching the instruments that detected it. The peak luminosity exceeded that of entire galaxies. This distinction between total energy and peak power is crucial and is sometimes conflated in popular accounts, leading to confusion. A stick of dynamite releases far less total energy than a slow-burning campfire over the course of a night, but the dynamite releases its energy in a millisecond, giving it a far higher instantaneous power. The physical consequences of the December 2004 event extended well beyond the magnetar itself. The expanding shell of radiation and relativistic particles produced a radio afterglow that was detected by ground-based radio telescopes beginning a few days after the event. This afterglow arose from the interaction between the ejected material and the surrounding interstellar medium, producing synchrotron radiation as electrons were accelerated in the resulting shock waves. The afterglow was observed for months, and its evolution provided independent constraints on the total energy released and the properties of the ejected material. The afterglow observations revealed an expanding ring-like structure, interpreted as the projection of a mildly relativistic shell of material expanding outward from the magnetar, with an initial velocity estimated at roughly 0.7 to 0.9 times the speed of light. This was the first time that a resolved expanding radio nebula had been observed in association with a magnetar giant flare, and it provided an important link between the magnetar phenomenon and the broader class of relativistic astrophysical outflows. The interaction of the gamma-ray pulse with Earth's atmosphere also produced detectable effects. The initial spike of the flare ionized the upper layers of Earth's atmosphere on the day side, producing a sudden increase in ionospheric electron density that was detected by very low-frequency radio receivers. The effect was comparable to that of a moderate solar flare, despite the fact that the source was 50,000 light-years away, rather than a mere 8 light minutes, the light travel time from the Sun. This ionospheric disturbance was measured by several ground-based monitoring networks and provided an independent confirmation of the extreme intensity of the event. The implications of this finding extend beyond the immediate context of the December 2004 event. If a magnetar giant flare of comparable or greater intensity were to occur at a much closer distance, say within a few hundred light-years, the resulting gamma-ray flux at Earth could be sufficient to cause significant depletion of stratospheric ozone, increased surface ultraviolet radiation, and potentially measurable biological effects. Some researchers have speculated that past magnetar giant flares from relatively nearby sources could have contributed to one or more of the mass extinction events recorded in Earth's geological history, though this remains speculative and difficult to test. The discovery of the December 2004 event also had implications for the interpretation of short-duration gamma-ray bursts. Before this event, it had been noted that some gamma-ray bursts detected from the direction of nearby galaxies within a few tens of megaparsecs had properties consistent with what a magnetar giant flare would look like if observed from extragalactic distances. The December 2004 event confirmed that magnetar giant flares can reach luminosities that, if the source were located in a nearby galaxy, would fall within the detection range of current gamma-ray burst monitors. This raised the question of what fraction of detected short-duration gamma-ray bursts might actually be extragalactic magnetar giant flares misidentified as gamma-ray bursts. Subsequent analyses have suggested that a small but non-negligible fraction of short gamma-ray bursts, perhaps a few percent, may be attributable to this mechanism, particularly those that lack an identified afterglow or host galaxy redshift. This has implications for the inferred rate of neutron star mergers and other progenitor models for short gamma-ray bursts, because any contamination of the sample by magnetar flares would bias the inferred rates. The question of what physical conditions within the neutron star led to the December 2004 event, and why it occurred when it did rather than at some other time, remains a topic of active research. In the months leading up to the giant flare, SGR 1806-20 had been in a state of enhanced activity, producing a much higher rate of ordinary bursts than its historical average. The persistent X-ray luminosity had also increased significantly, and the spin-down rate had accelerated, suggesting that the internal magnetic field was undergoing active evolution. This precursor activity is broadly consistent with the idea that the magnetic field was progressively building up stress in the crust, and that the giant flare represented the catastrophic release of this accumulated stress. However, the detailed triggering mechanism remains poorly understood. It is not clear whether the giant flare was initiated by a particular crustal fracture that cascaded into a global instability, or whether the instability was driven by processes in the fluid interior of the neutron star, where the magnetic field is anchored in a medium that supports complex magneto-hydrodynamic flows. The interior of a neutron star is a physical environment, unlike anything accessible to direct laboratory study. Beneath a thin outer crust, composed of a Coulomb lattice of neutron-rich nuclei immersed in a gas of degenerate electrons, there lies an inner crust where the nuclei become increasingly neutron-rich and eventually dissolve into a uniform fluid of neutrons, protons, and electrons at densities exceeding nuclear saturation density, roughly 2.7 times 10 to the 14 kilograms per cubic meter. At still higher densities, in the innermost core, the composition may include exotic states of matter such as hyperons, a Bose-Einstein condensate of pions or kaons, or deconfined quark matter, depending on which theoretical model of the strong nuclear force is correct. The equation of state of this ultra-dense matter, meaning the relationship between pressure, density, and temperature, is one of the central unsolved problems in nuclear physics and directly determines the maximum mass and radius of neutron stars, as well as their cooling behavior, oscillation modes, and response to magnetic stresses. For magnetars specifically, the interaction between the ultra-strong magnetic field and the various phases of matter in the interior creates additional complications. In the superconducting proton fluid that is believed to exist in the outer core, the magnetic field is confined to quantized flux tubes, analogous to the Abrikosov vortices in a Type II superconductor. The motion and rearrangement of these flux tubes is governed by the interaction between the flux tubes and the ambient neutron superfluid, which itself contains quantized vortex lines associated with the rotation of the star. The coupling and decoupling of these two systems of quantized structures is thought to play a role in the spin-down behavior of magnetars and may be involved in the generation of bursts and flares. This is a frontier area of theoretical physics where progress depends on advances in understanding the many-body physics of strongly interacting quantum fluids under extreme conditions. One observable consequence of the internal dynamics of neutron stars is the phenomenon of quasi-periodic oscillations, which were detected in the pulsating tail of the December 2004 giant flare. These oscillations, occurring at frequencies of approximately 18, 26, 29, 92, 150, 625, and 720 Hz, among others, were identified through Fourier analysis of the X-ray light curve and are interpreted as seismic oscillations of the neutron star excited by the giant flare, analogous to the ringing of a bell after it is struck. In the context of neutron stars, these oscillations are known as astroseismic modes, and their frequencies depend on the structure and composition of the star, including the density profile, the elasticity of the crust, the properties of the fluid core, and the magnetic field geometry. The detection of these modes was of considerable importance because it offered, for the first time, a set of observational constraints that could be directly compared with theoretical models of neutron star structure. Different equations of state for ultra-dense matter predict different frequencies and spacings for the seismic modes. So by matching the observed oscillation frequencies with theoretical predictions, it became possible to constrain the equation of state. This approach, sometimes called gravitational wave astroseismology, by analogy with helioseismology, the study of solar oscillations, is a powerful tool because it probes the deep interior of the neutron star, which is otherwise inaccessible to observation. The analysis of the quasi-periodic oscillations from SGR 1806-20 has been pursued by numerous research groups with somewhat varying conclusions, reflecting the complexity of the theoretical models and the limited precision of the data. The lowest frequency oscillations, near 18 to 30 Hz, are generally identified with torsional shear modes of the neutron star crust, which involve tangential deformations propagating around the star. The frequencies of these modes depend primarily on the shear modulus and density of the crust, and the observed values are roughly consistent with standard models of the crustal composition and structure. The higher frequency oscillations are more difficult to identify unambiguously and may correspond to coupled crust core modes, magnetoelastic oscillations in which the magnetic field provides a restoring force in addition to the elastic stress, or even modes of the trapped fireball itself. The magnetic field introduces a significant complication because it couples the crust to the core and alters the propagation characteristics of seismic waves, creating hybrid magnetoelastic modes whose properties depend on the field geometry, which is not directly observable. One of the persistent puzzles associated with SGR 1806-20 and magnetars more generally concerns the formation mechanism. The Duncan and Thomson model requires a neutron star born with a very short initial rotation period, on the order of 1 to a few milliseconds, in order for the convective dynamo to efficiently amplify the magnetic field to magnetar strengths. This implies that the progenitor star and the supernova explosion must have produced a neutron star with unusually high angular momentum. The reasons why some core collapse supernovae would produce rapidly rotating neutron stars, while others do not, remain unclear and are connected to the broader and largely unsolved problem of angular momentum transport in massive stellar interiors and during core collapse. Factors that may be relevant include the initial rotation rate and magnetic field of the progenitor star, the efficiency of angular momentum loss through stellar winds, the detailed hydrodynamics of the collapse and bounce, and the possible role of asymmetries and instabilities during the explosion. Numerical simulations of core collapse supernovae have made substantial progress in recent years, but still struggle to reproduce the observed properties of neutron stars, including their rotation periods and magnetic fields, from first principles. An alternative formation channel for magnetars has been proposed involving fossil magnetic fields, in which the ultra-strong field is not generated by a dynamo, but is inherited from a strongly magnetized progenitor star. Some massive stars are known to possess surface magnetic fields of several thousand Gauss, and magnetic flux conservation during core collapse could, in principle, amplify such a field to magnetar strengths. The viability of this channel depends on the survival of large-scale magnetic field structures during the turbulent convective stages of stellar evolution and during the collapse itself, which is uncertain. The two mechanisms are not mutually exclusive, and it is possible that both contribute to the magnetar population, with different magnetars owing their fields to different processes depending on the properties of their progenitor stars. The association of SGR 1806-20 with a cluster of massive stars is an important observational constraint on its formation. The cluster, sometimes referred to as the SGR 1806-20 cluster, or simply the LBV 1806-20 cluster, after one of its prominent members, contains several extremely luminous and massive stars, including a luminous blue variable with an estimated luminosity exceeding 10 to the 6 solar luminosities and an initial mass that may have exceeded 130 solar masses, making it one of the most massive stars known. The cluster also contains several Wolf-Rayet stars, which are evolved massive stars that have lost their outer hydrogen envelopes through intense stellar winds and represent a late stage in the evolution of stars with initial masses above roughly 25 solar masses. The age of the cluster is estimated at roughly 3 to 4 million years, which is consistent with the characteristic age of the magnetar and with the expected lifetime of the progenitor star, if it was indeed a very massive star. The presence of the magnetar in such a cluster supports the idea that magnetars form preferentially from the most massive stars, a suggestion that has been reinforced by the statistical association between magnetars and regions of recent massive star formation in the Milky Way and other galaxies. This connection to massive star formation raises questions about the rate at which magnetars are born and about the fraction of all neutron stars that are formed as magnetars. Current estimates suggest that the birth rate of magnetars in the Milky Way is approximately 1 per few hundred to few thousand years, which is a significant fraction, perhaps 10 to 30%, of the total core collapse supernova rate of approximately 2 per century. If this estimate is correct, then magnetars are not rare curiosities, but a common outcome of massive stellar evolution, and the reason that relatively few are observed at any given time is that their active lifetimes are short, on the order of 10,000 years, after which their magnetic fields have decayed sufficiently that they become quiescent and essentially undetectable with current instruments. This implies that the Milky Way may contain millions of dead magnetars that have passed through their active phase and are now indistinguishable from ordinary, faint, old neutron stars. The demographics of the magnetar population and its relationship to the broader population of neutron stars, including ordinary pulsars, central compact objects in supernova remnants, and the various classes of X-ray emitting neutron stars, is an active area of research that draws on population synthesis models, supernova rate estimates, and observational surveys across the electromagnetic spectrum. The aftermath of the December 2004 event for SGR 1806-20 itself was monitored extensively over the following years. The source's persistent X-ray luminosity, which had been elevated before the giant flare, initially dropped after the event and then gradually returned to approximately its pre-flare level over a timescale of years. The burst rate decreased markedly after the giant flare and remained low for an extended period, consistent with the idea that the giant flare had relieved a significant fraction of the accumulated magnetic stress. The spin-down behavior also showed changes in the post-flare period, with evidence for a transient increase in the spin-down torque, followed by a gradual return to the long-term trend. These post-flare changes provide additional constraints on the physical processes involved and are qualitatively consistent with the magnetar model, although the detailed interpretation depends on assumptions about the magnetic field geometry and the coupling between the crust, core, and magnetosphere that are not fully constrained by the available data. An important aspect of the December 2004 event that has received less public attention but is of considerable significance for fundamental physics is the constraint it places on Lorentz invariance violation. Some quantum gravity theories predict that the speed of light might depend very slightly on photon energy, with higher energy photons traveling either slightly faster or slightly slower than lower energy photons. This effect, if it exists, would be exceedingly small, proportional to the photon energy divided by the Planck energy, roughly 10 to the 19 giga-electron volts, and would be unmeasurable in laboratory settings. However, over cosmological or galactic distances, the tiny speed difference would accumulate, causing photons of different energies emitted simultaneously to arrive at different times. The December 2004 giant flare, with its very short rise time, its broad spectral range extending from radio to gamma-ray energies, and its source distance of 50,000 light-years, provided a natural laboratory for testing this prediction. Analyses of the arrival times of photons at different energies during the initial spike found no evidence for energy-dependent dispersion beyond what could be attributed to known astrophysical effects, placing limits on the energy scale at which Lorentz invariance might be violated that were comparable to or exceeded the Planck energy for certain forms of the hypothesized violation. This is a remarkable result because it means that a single astrophysical event, detected through conventional gamma-ray astronomy, provided constraints on physics at energy scales far beyond the reach of any particle accelerator. The broader scientific context in which the study of magnetars and their giant flares has developed deserves attention because it illustrates how progress in astrophysics often depends on the convergence of initially separate lines of investigation. The study of neutron stars, which began as a theoretical curiosity in the 1930s and became an observational reality in the 1960s, has benefited enormously from advances in nuclear physics, condensed matter physics, general relativity, plasma physics, and high-energy particle physics. The study of gamma-ray bursts, which began with the accidental detection of gamma-ray transients by the Vela military satellites in the late 1960s, surveillance satellites designed to monitor compliance with the Partial Nuclear Test Ban Treaty of 1963, drove the development of increasingly sophisticated gamma-ray detectors and the interplanetary network of burst monitors that was essential for localizing SGR events. The development of X-ray astronomy, which began with the detection of cosmic X-ray sources by sounding rocket experiments in the early 1960s, and matured through a series of increasingly powerful satellite observatories, including Uhuru, Einstein, Exosat, Ginga, Rosat, ASCA, Chandra, XMM Newton, and others, provided the persistent emission measurements and spectral data needed to characterize magnetars as a class. The development of radio interferometry, particularly very long baseline interferometry capable of milliarc-second angular resolution, made possible the detection and resolution of the radio afterglow from the December 2004 event. Each of these capabilities depended on decades of technological development, instrument design, and observational strategy that were not specifically aimed at understanding magnetars, but that proved essential when the phenomenon presented itself. The institutional and organizational context of this discovery is also worth noting. The detection and analysis of the December 2004 event involved dozens of research groups across multiple countries, using data from spacecraft operated by NASA, the European Space Agency, the Russian Federal Space Agency, and various other national and international agencies. The rapid communication of results was facilitated by the electronic preprint server AOK and by the astronomers' telegram and GCN circulars, systems designed for the rapid dissemination of time-sensitive astronomical information. The first detailed analyses were published within months of the event, and the interpretation has been refined through numerous subsequent papers over the following 2 decades. The collaborative and distributed nature of this scientific enterprise, involving theorists, observers, and instrument builders across traditional disciplinary and national boundaries, is characteristic of modern astrophysics and reflects the scale and complexity of the phenomena under investigation. It is instructive to consider the December 2004 event in the broader context of energetic astrophysical transients and the way our understanding of these phenomena has evolved over time. When gamma-ray bursts were first discovered in the late 1960s, there was no consensus on their distances, energies, or physical mechanisms. For nearly 3 decades, the nature of gamma-ray bursts was one of the great unsolved problems in astrophysics, with literally hundreds of proposed models ranging from nearby cometary impacts to collisions between exotic stellar remnants in distant galaxies. The resolution of this problem came gradually, through the accumulation of observational data from increasingly capable instruments, the discovery of afterglows in 1997 that allowed host galaxies to be identified and distances to be measured, and the development of the collapsar and compact merger models that are now widely accepted. The history of soft gamma repeaters and magnetars follows a parallel but distinct trajectory. Initial detection and puzzlement, the proposal of a theoretical model that seemed extreme at the time, gradual accumulation of supporting evidence, and eventual broad acceptance, punctuated by rare spectacular events that provided critical tests of the theory. The magnetar model, as of the time of the December 2004 event, had already gained substantial support but was not yet universally accepted. Some researchers favored alternative models, including accretion-powered scenarios and models involving strange quark stars rather than neutron stars. The December 2004 event did not definitively rule out all alternatives, but the combination of the event's properties, including its energy, spectrum, temporal structure, quasi-periodic oscillations, and radio afterglow, with the prior evidence from the 2 earlier giant flares and the broader phenomenology of SGR and anomalous X-ray pulsar activity, created a body of evidence that was most naturally and comprehensively explained by the magnetar model. By the end of the first decade of the 21st century, the magnetar interpretation was widely accepted within the astrophysics community, and the term magnetar had entered the standard vocabulary of the field. The continued study of SGR 1806-20 and other magnetars has been facilitated by new observational capabilities deployed since 2004. The detection of magnetar-like behavior from previously known rotation-powered pulsars and the discovery of new magnetars through their transient X-ray and gamma-ray emission have expanded the known population to roughly 30 confirmed or candidate magnetars as of the early 2020s. The detection of rapid radio bursts from the galactic magnetar SGR 1935+2154 in April 2020, coincident with a hard X-ray burst, established a direct observational link between magnetar activity and at least some fast radio bursts, a class of extragalactic radio transients discovered in 2007 whose physical origin had been debated. This connection was one of the most significant developments in astrophysics in recent years, because fast radio bursts are detected from cosmological distances and their potential association with magnetars would have profound implications for the demographics of magnetars in other galaxies, and for the use of fast radio bursts as probes of the intergalactic medium. The connection between the December 2004 giant flare and the emerging field of gravitational wave astronomy is more tenuous but worth mentioning. The seismic oscillations of the neutron star excited by the giant flare, if sufficiently energetic, would produce gravitational waves at the frequencies of the oscillation modes. However, the predicted gravitational wave amplitudes for a magnetar at the distance of SGR 1806-20 are far below the sensitivity thresholds of current detectors such as LIGO and Virgo. A similar event from a much closer magnetar within a few kiloparsecs might produce detectable signals, and this possibility motivates efforts to improve the sensitivity of gravitational wave detectors and to develop search algorithms specifically targeted at magnetar activity. The detection of gravitational waves from a magnetar giant flare would provide a direct probe of the neutron star interior structure that is complementary to and independent of the electromagnetic observations and would represent a significant milestone in multi-messenger astrophysics. Returning to the event itself and its place in the history of high-energy astrophysics, the December 2004 giant flare from SGR 180620 occupies a unique position. It was the most luminous transient event detected from a compact object within the Milky Way in the era of modern observational astronomy. Its study has contributed to our understanding of ultra-strong magnetic fields, the behavior of matter under extreme conditions, the structure of neutron stars, the physics of relativistic outflows, and the demographics of stellar remnants. It has served as a test case for theories of quantum electrodynamics in strong fields, for models of seismic oscillations in compact stars, and for limits on new physics beyond the Standard Model. It has connected the study of galactic magnetars to the extragalactic gamma-ray burst population, and more recently, to the phenomenon of fast radio bursts. And it has illustrated, in a particularly vivid manner, the extreme violence that nature can produce in the remnants of massive stars. The scientific study of SGR 1806-20 is ongoing. New observations with current and planned X-ray and gamma-ray satellites continue to monitor the source's persistent emission and burst activity. Theoretical models of magnetar interiors and magnetospheres are being refined through increasingly sophisticated numerical simulations that incorporate general relativistic magnetohydrodynamics, quantum electrodynamic effects, and realistic equations of state for ultra-dense matter. The growing population of known magnetars and magnetar candidates provides an expanding database against which theoretical predictions can be tested statistically, rather than on a case-by-case basis. And the possibility that future giant flares will be detected, either from SGR 1806-20 or from other magnetars, with the benefit of next-generation instruments and the addition of gravitational wave and neutrino detection capabilities, ensures that this field will continue to produce important results. The distance scale deserves further elaboration because the numbers are central to the analysis. 50,000 light-years is roughly half the diameter of the Milky Way's disk, placing SGR 1806-20 well on the far side of the galaxy as seen from Earth. This means that the gamma-ray photons that arrived on December 27, 2004 had been traveling since roughly 48,000 BCE by the conventional calendar, a time when modern humans were in the midst of the Upper Paleolithic, tens of thousands of years before the development of agriculture, writing, or cities. The neutron star that produced this event had itself formed thousands of years before that, in a supernova explosion whose light, if it was visible from Earth at all given the intervening dust, would have appeared as a temporary new star in the sky of Sagittarius at some unknown point in deep prehistory, unrecorded and unnoticed. The giant flare itself, the catastrophic magnetic reconfiguration that released 250,000 years' worth of solar energy in 1/5 of a second, occurred while the photons from the original supernova were still in transit, still thousands of light-years from Earth. By the time the flare's radiation reached our instruments on that December evening, the magnetar had already continued evolving for 50,000 years, spinning down, cooling, perhaps producing additional bursts and flares that we will detect in the coming centuries as their light arrives. This temporal disconnect, inherent in any observation of distant astrophysical objects, is a fundamental feature of astronomy that distinguishes it from laboratory sciences and introduces layers of interpretation that must be navigated carefully. The environment immediately surrounding SGR 1806-20 is itself of considerable interest. The magnetar is embedded within or near the massive star cluster mentioned earlier, a region of active and recent star formation containing some of the most luminous and massive stars in the galaxy. This environment is pervaded by intense ultraviolet radiation, strong stellar winds, and a complex interstellar medium shaped by the energy input from the massive stars. The supernova that created the magnetar would have added to this energy input, sweeping up surrounding material into an expanding shockwave that may still be detectable as a supernova remnant. Though the identification of a specific remnant associated with SGR 180620 has been complicated by the crowded and confused nature of the field near the galactic center. The proximity of the magnetar to other massive stars raises the question of whether the intense radiation and wind environment has any effect on the magnetar's behavior. Though at the distances involved, typically several light-years, the direct influence of the neighboring stars on the neutron star is negligible. The detection capabilities that made the observation of the December 2004 event possible are worth examining in some detail because they illustrate the technological trajectory that has shaped high-energy astrophysics. The first detections of cosmic gamma-ray sources in the 1960s were made with small scintillation detectors aboard Vela satellites and other spacecraft. With effective areas of a few hundred square centimeters and limited spectral and temporal resolution. By the time of the March 1979 event from SGR 052666, the instruments available included the CONUS experiment on the Venera interplanetary probes, which used sodium iodide scintillation detectors to measure gamma-ray burst spectra and light curves with time resolution of the order of milliseconds. The Compton Gamma Ray Observatory, launched in 1991, carried the Burst and Transient Source Experiment, BATSI, which detected thousands of gamma-ray bursts and SGR bursts over its 9-year mission, establishing the isotropic sky distribution of classical gamma-ray bursts and providing the statistical framework for understanding their spatial distribution. The Rossi X-ray Timing Explorer, launched in 1995, provided microsecond time resolution for X-ray observations that was essential for detecting the quasi-periodic oscillations in the tails of giant flares. The BeppoSat satellite, launched in 1996, pioneered the rapid localization and afterglow detection of gamma-ray bursts, techniques that were subsequently refined and applied to magnetar events. The Integral Observatory, launched in 2002, provided the broadband gamma-ray spectroscopy and imaging that captured some of the most detailed data on the December 2004 event. Each of these missions represented an increment in capability that built on the scientific questions raised by previous observations and the technological lessons learned from previous instruments. The ground-based follow-up observations of the December 2004 event were equally important. Radio observations with the Very Large Array, the Australia Telescope Compact Array, and various VLBI networks tracked the expanding radio afterglow for months, providing morphological, spectral, and polarimetric data that constrained the properties of the ejected material and the surrounding medium. Infrared observations, necessary because of the heavy dust extinction along the line of sight, provided constraints on the persistent counterpart and the associated star cluster. The multi-wavelength nature of the follow-up campaign, involving facilities across the electromagnetic spectrum and around the globe, exemplified the collaborative approach that has become standard for major astrophysical transients. A thread that runs through the entire history of magnetar research, and that is exemplified by the December 2004 event, is the role of rare, high-impact events in driving scientific understanding. In many areas of science, progress comes through the accumulation of large statistical samples and the systematic analysis of patterns within those samples. In magnetar physics, the giant flares are so rare, with only 3 definitively identified in over 40 years of observation, that each one represents a unique opportunity to test and refine theoretical models. The information content of a single well-observed giant flare, with its rich temporal, spectral, and spatial structure, exceeds that of thousands of ordinary SGR bursts. This has important methodological implications. The analysis of giant flares requires different statistical and interpretive approaches than the analysis of ordinary bursts, and the theoretical models must be capable of explaining not just the average behavior of the source, but the detailed properties of individual exceptional events. The rarity of giant flares also means that the current understanding of the phenomenon is based on a very small sample, and any general conclusions drawn from 3 events must be treated with appropriate caution. The next giant flare, whenever and wherever it occurs, will provide a critical additional data point that may confirm, refine, or challenge the existing theoretical framework. The broader implications of the magnetar phenomenon for our understanding of stellar evolution, compact object physics, and the high-energy universe continue to expand. The discovery of transitional objects that exhibit behavior characteristic of both magnetars and ordinary pulsars, sometimes switching between the two modes, has blurred the previously sharp boundary between these categories and suggests a continuum of magnetic field strengths and evolutionary histories among neutron stars. The detection of magnetar-like outbursts from previously quiescent neutron stars has expanded the range of known magnetar behavior and suggests that some neutron stars may harbor hidden strong magnetic field components that are normally dormant, but can occasionally manifest through transient activity. The theoretical development of models for the coupled evolution of magnetic fields, rotation and thermal structure in neutron stars has progressed significantly, though fundamental questions about the equation of state, the magnetic field topology, and the dissipation mechanisms remain open. The energy scale of the December 2004 event invites comparison with other phenomena that operate at similar scales but through entirely different physical mechanisms. The total energy released in the giant flare, roughly 10 to the 39 to 10 to the 40 joules, is comparable to the kinetic energy of a large asteroid impact, or to the total luminous energy output of a typical Type Ia supernova. It is several orders of magnitude less than the gravitational binding energy released in a core collapse supernova, but several orders of magnitude more than the rotational energy of the magnetar, which at the current rotation period of 7.56 seconds is only about 10 to the 36 joules. This last comparison is significant because it confirms that the energy source for the giant flare cannot be rotational energy, as it is for ordinary pulsar emission, but must be magnetic energy, consistent with the magnetar model. The magnetic energy reservoir, estimated at 10 to the 40 joules or more for a magnetar strength field, is sufficient to power several giant flares and a very large number of ordinary bursts over the active lifetime of the source, consistent with the observed activity levels. The question of whether the December 2004 event represents an upper limit on the luminosity achievable by a magnetar giant flare, or whether even more powerful events are possible, remains open. Theoretical models suggest that the maximum energy of a giant flare is set by the total available magnetic energy, which depends on the field strength, the field geometry, and the volume of the neutron star. For the most extreme theoretical field strengths, the maximum energy could be several times 10 to the 40 joules, somewhat exceeding the inferred energy of the December 2004 event. It is therefore possible that more energetic giant flares occur in nature, but have not yet been observed, either because they are extremely rare or because they occur in other galaxies where they might be detected as short gamma-ray bursts, rather than recognized as magnetar flares. The rate of giant flares in the Milky Way is estimated at very roughly once per 30 to 50 years, based on the 3 observed events over about 40 years of monitoring, though this estimate is highly uncertain given the small number statistics. In other galaxies, the detection of giant flares is limited by distance. Only the most luminous events can be detected from extragalactic distances, and even then, they must be distinguished from genuine gamma-ray bursts, which is not always straightforward. The interaction between the theoretical and observational communities in the study of magnetars provides an instructive example of how scientific understanding develops in practice. The magnetar model was proposed in 1992, before the crucial observational confirmations of the late 1990s and 2004. At the time of its proposal, the model was regarded by many as speculative, partly because the magnetic field strengths it invoked were so far beyond those of known pulsars that they seemed implausible, and partly because the observational evidence was limited to a handful of SGR sources with relatively sparse data. The proponents of the model, Duncan and Thompson, continued to develop the theory in considerable detail, making increasingly specific and testable predictions about the properties of magnetar bursts, persistent emission, spin-down behavior, and seismic oscillations. When these predictions were subsequently confirmed by observations, particularly the detection of ultra-strong magnetic fields inferred from spin-down measurements of anomalous X-ray pulsars, a related class of X-ray sources now understood to be magnetars in a different evolutionary state, the model gained broad acceptance. The December 2004 giant flare, with its quasi-periodic oscillations matching the predicted frequencies of neutron star seismic modes, provided what many regarded as the most compelling single piece of evidence for the magnetar model, because it connected the external electromagnetic observations directly to the internal structure of the neutron star in a manner that no alternative model could readily reproduce. This pattern, in which a theoretical prediction precedes and then guides the interpretation of subsequent observations, is one of the most productive modes of scientific advance, but it carries risks. There is a natural tendency for observations to be interpreted within the framework of the dominant theoretical model, and for alternative interpretations to receive less attention than they might deserve. In the case of magnetars, the dominance of the Duncan-Thompson model has been so complete that alternative models, such as those invoking quark stars or fallback accretion disks, have been relatively marginalized, even though they have not been definitively ruled out by the available data. The sociology of scientific communities plays a role here. Once a model achieves a critical mass of supporters and a sufficient track record of successful predictions, it becomes the default framework within which new observations are analyzed, and the burden of proof effectively shifts to the proponents of alternatives. This is not necessarily a failure of the scientific process, but rather a reflection of the finite cognitive resources of any community and the pragmatic need to focus effort on the most promising lines of investigation. Nonetheless, awareness of this dynamic is important for maintaining intellectual openness to the possibility that the current understanding may be incomplete or in need of revision. The cultural and institutional context of high-energy astrophysics at the time of the December 2004 event also shaped how the discovery was communicated and perceived. The event occurred during a period of rapid expansion in multi-wavelength and multi-messenger astronomy, driven by the deployment of a fleet of space-based observatories and the development of ground-based facilities for gravitational wave detection, neutrino astronomy, and ultra-high-energy cosmic ray observation. The concept of time-domain astronomy, the systematic study of transient and variable phenomena, was emerging as a major theme in the field, motivated partly by the scientific potential of events like the December 2004 giant flare, and partly by the technological capabilities of new survey instruments capable of monitoring large areas of sky with high cadence. The December 2004 event served as a demonstration case for the scientific value of rapid multi-wavelength follow-up of astrophysical transients, an approach that has since become standard practice and has been formalized through networks of telescopes and automated alert systems. The event also had implications for the assessment of astrophysical hazards to life on Earth. The ionospheric disturbance caused by the December 2004 flare, while scientifically interesting, had no practical consequences for life on Earth's surface. However, the fact that a detectable ionospheric effect was produced by a source at 50,000 light-years prompted calculations of what would happen if a similar event occurred at much shorter distances. These calculations showed that a giant flare of comparable luminosity occurring within about 10 light-years would deliver a gamma-ray fluence at Earth sufficient to significantly deplete the ozone layer, potentially leading to elevated surface ultraviolet radiation, disruption of photosynthetic organisms, and cascading ecological effects. While the probability of a magnetar giant flare at such close range is extremely small, given the current absence of any known magnetar within several thousand light-years, the exercise illustrates the broader point that compact stellar remnants, through mechanisms that were unsuspected before the magnetar era, can influence their galactic environment at distances far greater than might naively be expected. The relationship between the December 2004 event and the Indian Ocean earthquake and tsunami that occurred on December 26, 2004, one day earlier, has been a source of persistent public confusion that is worth addressing directly. The two events are entirely unrelated. The earthquake, which occurred along the Sunda megathrust fault off the coast of Sumatra, was caused by tectonic forces within Earth's crust and had nothing to do with astrophysical processes. The temporal coincidence is just that, a coincidence, and the gamma-ray pulse from SGR 180620 could not have triggered or influenced the earthquake in any way, because the energy deposited in Earth's atmosphere by the flare was negligible compared to the energy scales of seismic processes, and in any case, the gamma rays did not penetrate below the ionosphere. Nevertheless, the proximity of the two events in time led to widespread speculation and misinformation in popular media and on the internet, illustrating the challenges of communicating scientific information accurately in an environment where coincidences are easily misinterpreted as causal connections. Looking at the broader picture, the study of SGR 1806-20 and its December 2004 giant flare sits within a long tradition of astrophysical research in which extreme objects and events serve as natural laboratories for testing fundamental physics under conditions that cannot be replicated in terrestrial facilities. Neutron stars in general, and magnetars in particular, probe physics at the intersection of general relativity, quantum chromodynamics, quantum electrodynamics, and condensed matter physics in regimes of density, pressure, temperature, and magnetic field strength that are utterly inaccessible to direct experiment. The information extracted from observations of these objects, through careful analysis and comparison with theoretical models, contributes to our understanding of the fundamental forces and the behavior of matter under extreme conditions. The December 2004 event, as the most extreme example of magnetar activity ever observed, pushed these boundaries further than any previous observation and set the stage for future discoveries that will continue to illuminate the physics of the most extreme environments in the universe. The ongoing observations of SGR 1806-20 in the years since the giant flare have revealed a source that continues to evolve. Its burst rate, which was elevated before the giant flare and dropped afterward, has fluctuated over time, with periods of enhanced and reduced activity that may reflect the continuing evolution of the magnetic field structure in the aftermath of the catastrophic reconfiguration. The persistent X-ray flux has shown long-term variability that is not fully understood but is consistent with changes in the magnetospheric structure or the rate of internal heating. The spin-down rate has also varied, with episodes of spin-up and spin-down that may be associated with changes in the external torque due to variations in the magnetospheric current flow, or with internal processes such as the transfer of angular momentum between the superfluid core and the rigid crust. These ongoing observations, while less dramatic than the giant flare itself, provide a continuous stream of data that constrains the long-term evolution of magnetars and tests the predictions of theoretical models on timescales of years to decades. The theoretical understanding of how the ultra-strong magnetic field of a magnetar decays and evolves over time has advanced significantly in recent years through numerical simulations that follow the coupled evolution of the magnetic field, the temperature, and the rotational dynamics of the neutron star. These simulations show that the magnetic field evolves through a combination of ohmic decay, in which electrical currents in the crust dissipate through resistive effects, Hall drift, in which the magnetic field is advected and distorted by the motion of electrons in the crustal lattice, and ambipolar diffusion, in which the magnetic field migrates through the fluid core as the charged particles drift relative to the neutral particles. The interplay between these processes produces a complex evolution in which the large-scale dipolar field generally decays over timescales of thousands to tens of thousands of years, while smaller-scale field structures can be generated and amplified through the Hall cascade, a process analogous to the turbulent cascade of energy in fluid dynamics, but operating in the domain of magnetic field topology. The energy dissipated through these processes heats the neutron star crust and provides the persistent X-ray luminosity that is a defining characteristic of active magnetars. These simulations make predictions for the evolution of the spin-down rate, the surface temperature distribution, and the burst activity as functions of time that can in principle be compared with the observed properties of magnetars of different ages. The observed correlation between spin-down inferred magnetic field strength and characteristic age among the known magnetar population provides some support for the general picture of magnetic field decay, though the scatter in the observed properties is large and reflects both the intrinsic diversity of the population and the uncertainties in the theoretical models. The identification of older, less active magnetars and the detection of magnetar-like behavior from sources that were previously classified in other categories continues to expand the empirical baseline for these comparisons. The study of neutron star interiors through the seismic oscillations detected in the December 2004 event has spawned a subfield sometimes called magnetar seismology or neutron star asteroseismology. The goal of this field is to use the observed oscillation frequencies, their damping times, and their relative amplitudes to constrain the properties of the neutron star interior, including the density profile, the composition, the superfluid and superconducting properties of the core matter, and the magnetic field geometry. This is conceptually analogous to helioseismology, in which the observed frequencies of solar oscillations are used to probe the internal structure of the Sun, and to terrestrial seismology, in which the propagation of seismic waves through Earth's interior reveals the properties of the mantle and core. In the neutron star case, the analysis is considerably more complex because of the strong coupling between the elastic, magnetic, and fluid degrees of freedom, and because the data set is limited to the frequencies and approximate amplitudes measured during a few giant flares. Nonetheless, the identification of specific oscillation modes with predicted crustal shear modes and magnetoelastic modes has provided meaningful constraints on the shear modulus of the neutron star crust, and through this, on the properties of neutron-rich matter at subnuclear densities. The shear modulus of the neutron star crust depends on the composition and structure of the crustal lattice, which in turn depends on the nuclear physics of extremely neutron-rich matter. At the densities found in the inner crust, roughly 10 to the 14 kilograms per cubic meter, the equilibrium nuclear composition includes extremely neutron-rich nuclei with mass numbers of several hundred to 1,000, surrounded by a sea of free neutrons. Near the base of the crust, at the transition to the fluid core, the nuclei may adopt exotic non-spherical shapes, sometimes described metaphorically as nuclear pasta, due to their resemblance to various types of Italian pasta, sheets, rods, tubes, and more complex topologies. The mechanical properties of this nuclear pasta layer, its shear modulus, breaking strain, and viscosity, are thought to play a critical role in determining the threshold for starquakes and the details of the seismic oscillation spectrum. Calculating these properties from first principles is an extremely challenging problem in nuclear many-body theory that has been addressed through a variety of computational techniques, including molecular dynamics, simulations of dense nuclear matter, with results that suggest the nuclear pasta phase may be the strongest material in the known universe in terms of its breaking strain, exceeding that of steel by roughly 10 orders of magnitude. The connection between the nuclear physics of the neutron star crust and the observable properties of magnetar giant flares is one of the most remarkable interdisciplinary linkages in modern astrophysics. An event observed through gamma-ray telescopes orbiting Earth provides information about the mechanical properties of matter at nuclear density through a chain of reasoning that passes through electrodynamics, general relativity, elasticity theory, and nuclear many-body physics. This chain is long, and each link introduces uncertainties. So the constraints obtained are model-dependent and should be interpreted with appropriate caution. Nonetheless, the fact that such constraints can be obtained at all from astronomical observations of objects 50,000 light-years away is a testament to the power of the physical theories that connect these disparate scales, and to the extraordinary properties of the event that generated the data. The future of magnetar research will be shaped by several anticipated developments. New X-ray observatories with higher sensitivity, better spectral resolution, and faster timing capabilities will provide improved data on the persistent and burst emission from known magnetars and enable the detection of fainter or more distant sources. Proposed gravitational wave detectors with improved sensitivity in the kilohertz frequency range, such as the third-generation ground-based detectors, Einstein Telescope and Cosmic Explorer, may be capable of detecting the gravitational wave emission associated with magnetar seismic oscillations, providing a completely independent probe of the neutron star interior. The continued monitoring of known magnetars will extend the baseline for studying their long-term evolution and will increase the probability of detecting the next giant flare with a comprehensive suite of instruments. And the continued development of theoretical models, driven by advances in computational power and in our understanding of the fundamental physics of dense matter and strong fields, will sharpen the predictions against which future observations can be tested. The December 27, 2004 event from SGR 1806-20 remains, nearly 2 decades after its occurrence, the most powerful explosion ever detected from a compact stellar remnant and the most luminous transient event observed from within the Milky Way in the era of modern astronomy. Its study has advanced our understanding of magnetic fields in astrophysics, the physics of matter at extreme densities, the seismology of neutron stars, the demographics of stellar remnants, and the connections between galactic transients and extragalactic phenomena. It has provided constraints on fundamental physics at energy scales far beyond the reach of laboratory experiments. And it has demonstrated, in a manner that no previous observation had, the extreme energy that can be released through the reconfiguration of magnetic fields in the most magnetized objects in the known universe. The magnetar SGR 180620 itself continues to evolve, its magnetic field slowly decaying, its rotation gradually slowing, its crust healing from the catastrophic fracture that produced the giant flare, while accumulating new stresses that may eventually lead to another period of enhanced activity, or even another giant flare, an event that astronomers around the world now have the instruments and the theoretical framework to observe and interpret with far greater precision than was possible in 2004. Whether such an event occurs in the coming years or not for centuries, the December 2004 flare stands as a landmark in our understanding of the extreme physical processes that occur in the remnants of massive stars and of the extraordinary violence that the universe is capable of producing from objects barely 20 kilometers across.